Hello everybody, my name is Yigong Zhang. This summer I have been doing research with Professor He's research group on the project Semiconductor Gamma Ray Detector Properties under High Flux Radiation. Here's the outline of what I'm going to present today. First, I will give you the motivation to study this problem. Then I will introduce the important concept of trapping and detrapping. Then I will give the Monte Carlo simulation. Finally, I will try to fit the Monte Carlo simulation and the experiment data and to give the final results of the trapping and detrapping time. Now let's get started with the motivation. According to Shapley-Riemann theorem, the induced charge equals to the negative generated charge times to the change of the weighting potential. So theoretically, the induced charge is linear with the generated charge. So this linearity can give us the information of the generated charge. But we know that trapping might undermine this linearity and lead to wrong information about the generated charge and give us the wrong information about the interaction happens at the detector. So what's trapping and detrapping? So trapping and detrapping are resulted from the impurities. And we know that in CZT, the cadmium, zinc, telluride, there is a strong correlation between the trapping effect and the tellurium inclusion. Here's the schematic diagram of the impurity and the trapping. We know that if we have purified material, and the energy band will be distinct, and it will be a straight line in this diagram. So we know that the electrons won't be trapped or stopped when they travel. But when the impurity involved, we can see here, the impurity will introduce something like potential well that might trap the electrons and affect its drifting transportation. So this effect will give us the trapping problem. And then we need to physical quantity to describe the trapping and detrapping. So we use the trapping time, and we note it as tau t. Trapping time is the mean free time, which equals to 1 over the density of traps per volume and times the cross-section and times the velocity. And the detrapping time we note as tau d, and from Fermi-Dirac distribution function, we know that tau t over tau d equals to this expression. Since trapping and detrapping are described by the probability, so the best way to simulate it is the Monte Carlo simulation, I believe. So how do I model the trapping? Our generated random number indicates when the electrons will be trapped. And if the time is smaller than the subinterval, then it will be trapped in this subinterval. If it's longer than this subinterval, it won't be trapped. In this diagram, the red dot means it will be trapped. Black dot means it won't be trapped. So it's the same story for the detrapping. Our generated detrapping number and indicate when it will be detrapped. If it's smaller than the subinterval, it will be the green dot, and it will be detrapped. And if it's longer than the subinterval, it won't be detrapped. It's noted as the black dot. Then I can calculate the induced charge by the Shapley-Riemann theorem at each time instant by the expression below. Since I know where the carriers are, then I can track the carriers. So at the beginning, the interaction happens at the depth equals to 0.5 centimeter. And then the electrons were drifted to the anode side, which is the right side of the diagram. And the holes were drifted to the left side. We can see here, electrons have a much higher mobility than holes. Then, because of the fast trapping and detrapping time, the electrons were like a Gaussian distribution. But we can see the holes are trapped around where the interaction happens. Finally, when the electrons are collected at the anode side, the holes are still around the interaction where the interaction happens. Then I try to use the simulation, use simulation to compare with the experiment data to give me the trapping and detrapping type. Here's the plot with fixed detrapping type. Here I just want to have a sense of how the trapping time affected the waveform. Then I change the trapping time. Here's the plot of fixed trapping time and the changing detrapping time. Then I try to have the sense of how the detrapping time affects the waveform. Then I simulate at different depths for the combinations listed below. What's the result? The blue block give me good fitting results, but the red block can't. Then at a more precise pattern, I got the results listed here. It's 3000 nanoseconds for the trapping time and 17 nanoseconds for detrapping time. This will give me the fitting results in this plot. So this is the best single trap model fitting results. How about the amplitude? We know that the amplitude changes with depths. In this plot, the blue lines is the amplitude generated from the simulation, and the red lines are from the experiment data. We can see that they can't fit at all. Then I have to introduce another trap to govern the amplitude. Thus, I have two traps. One is 3000 nanoseconds for the trapping time and 17 nanoseconds for detrapping time. And the other trap is 10,000 nanoseconds for the trapping time and infinitely long for detrapping time. Infinitely long means it won't be detrapped at all. So this gives me the fitting results below. Then we can see here, this gives me a much better fitting results for the amplitude. So the final result is, for the first trap, the trapping time is 3000 nanoseconds and 17 nanoseconds for the detrapping time. And for the second trap, the trapping time is 10,000 nanoseconds and infinitely long for detrapping time. Now I need to thank Professor Zhong He and the College of Engineering giving me this chance to do research here, and also my advisor Miesher and Yuefeng Zhu.